Okay.
Can everyone hear me through the microphone? Fantastic, thank you. So my name is Abby, I am the president of the Physics Society, and we are very fortunate to have Jonathan coming to give a talk for us today. So we've got some people from Climate Action Society here with us as well, and then the Physics Society too. So just a little introduction on Jonathan. He did his undergraduate maths at Cambridge, part 3 maths. You've travelled for a bit, you did your PhD here with Robin Tucker. You're a postdoc in Paris, a postdoc here. You worked in Oslo, was a postdoc in Bangor, a postdoc in Lancaster, and now you're finally here as a lecturer in mathematical physics and a member of the Cockcroft Institute of Accelerated Science. And you're going to be doing a talk. What's your talk called today?
Oh my God, I've got to try and remember now. Nuclear bombs while solar and wind sail. Did everyone get that in the end? Good.
Yeah. So thank you all. Yeah, thank you all for coming to watch the talk, and please give a warm welcome for Dr. Jonathan Greatus.
Thank you. Okay, let's shrink that so I'm not. Okay, we're going to start with a couple of Mentimeter questions. How do I? That one as well. And go to present, get the full screen. Right, so what in your opinion were the 3 worst disasters for nuclear power? So I think you can vote as many times as you like. Okay, some people who've spoken to me know my thinking, but I thought you might like some thoughts about that. Okay, so Chernobyl, obviously, Fukushima, very good. I'll wait till it gets to about 13 or something. You can vote several times, I think, so. Hey, one person's put Hinkley Point, very good. Oh, I love these, aren't they fun? Okay, so obviously Chernobyl's the big one. Some people will remember, will have been alive during Chernobyl. Everyone will have been alive during Fukushima. Only one person has put Hinkley Point C. I would imagine that not many of you have heard of Vogt. Electric generating plants 3 and 4, and nobody can pronounce the other one. Is anyone Finnish here, by the way? What? I thought physicists always spend their spare time learning Finnish. Okay, brilliant. So, right, what are the biggest problems for nuclear energy? Oh, very good. Somebody knows my thinking here. Nuclear waste, very good. Nuclear proliferation. Mainly people are concerned with nuclear waste. Okay. It's been too long since we've had a decent nuclear accident that people aren't worried about that one that much. Okay, what if I, option 4, option 5. What if I fill in option 4 and option 5? Okay, so vote again and see where we're up to. Well, with extra option, one person has now put nuclear accident. Okay, that's fine. Okay, you are along my lines of thinking. You might have read my abstract. Okay, so if we go to my talk, and is that present? No. Where's the present mode? Okay, so I'm Jonathan Greatest, as it was said. It's nicely introduced. Just like to point out that all the images are from Wikipedia, unless otherwise stated, as is most of the talk. Okay, if you're entering your fourth year next year, don't do your literature review like this. Okay, but hopefully it's not my area of research, but I've got very you know how you chase YouTube videos, and the more they wind you up, the more you chase them. So I've been watching lots of YouTube videos about how wonderful nuclear power is, and I'm thinking, I don't agree with this. So I decided to do this talk. So let's have a look at these problems with nuclear. So the first one was nuclear power is the problem with nuclear accidents. So you'll get the people in the nuclear industry that say nuclear power is safe. And you think, no, it's not. People have died because of nuclear power. So I put an asterisk there. It's safe enough, okay? It is, there have been several accidents with definite loss of life. There's no doubt about that. The lowest estimate is about 40, with 32 odd from Chernobyl and a couple with another couple of accidents, to tens of thousands. Because the problem is that when you have a nuclear accident, a lot of people are affected a little, okay? And it's very hard to track those numbers. But even at the large estimate of tens of thousands, per kilowatt of energy, kilowatt hour of energy, it's actually one of the lowest forms of energy, death per energy produced. And in fact, nuclear power saves lives. More people die from, and this isn't accidents and stuff like this is just from air pollution. More people die from the air pollution of coal. Coal is an absolute disaster. Biomass is pretty grim. So just by having nuclear power stations, it saves lives. We used to think there was no safe level of radiation. However, a series of experiments, experiments very much in inverted commas there, such as exploding bombs during war and during tests, accidental releases of radiation, deliberately testing radiation on soldiers. I didn't realize the US government was quite keen on that during the 50s and 60s. We now know the body is much better at repairing itself from low-level nuclear, low-level doses of radiation. So long as you're below a certain amount, which most people are, fortunately, even during an accident, most people's bodies will repair themselves. I'd like to see these experiments get past our ethics committees today. What about proliferation? Well, it does happen. There's no doubt about it. It is likely that nuclear power has led to nuclear weapons. It certainly didn't for the big five, US, UK, France, Russia, and China, who developed bombs first and then tried to justify their research into nuclear weapons by having nuclear power. But India and Pakistan did it the other way around. They developed the nuclear power first, and although if you're part of the IAEA, you're not allowed to transfer equipment or machinery between civilian. You're not allowed to transfer stuff from civilian to weapons manufacture. There, you are allowed to transfer the people, so that the skills that people develop during in the handling of nuclear materials or refining and processing has been necessary to build bombs. So if you have a nuclear industry, it's much easier to produce bombs. And the US certainly thinks so, otherwise they wouldn't be spending so much effort stopping Iran from having a nuclear power program if there was no link whatsoever. Waste, well, there certainly is waste, okay, but it is contained. It's not brilliant, it's contained. There is ideas for long-term storage. but this is a problem so there's ideas, but in reality, the main way of dealing with waste is to just ignore it, okay? We fill up these big baths full of tanks full of water, and we put the waste in there, and we hope that our grandchildren will work out a way of solving it. But it should be really noted that more radiation is actually released from burning coal. Coal is naturally radioactive. When you burn it, all that radioactive material just goes into the atmosphere. So, hooray for nuclear power. And we can all go home now. Okay, so we can cope with the problems of nuclear power, or at least hide it under the carpet for a few hundred years and hope it will get solved later. So let's build lots of nuclear power stations. What's the problem? Well, here are my 3 disasters, okay? Delayed and over budget. So the Voigt electrical generating plant in Georgia applied first in 2006, construction started in 2009. The predicted date was 2016. Okay, it still hasn't been built. Okay, they're loading the fuel now. The cost ballooned from 14 billion to 30 billion. Okay, and the total time 16 years if it does start as planned, currently planned. So that was a bit of disaster. How about are you sure there's no one Finnish here? Olkiluoto nuclear power station in Finland. Okay, so that was described as the example of everything that can go wrong in economic terms with new reactors. Okay, it was started in 2005, predicted to start in, so the construction started in 2005, predicted date 2010, 3 billion. Actual, well, they're just getting it started now. Okay, so you see that it's massively delayed and massively over budget. Okay, total 17 years. 17 years from when the permit was given. So that's not 17 years when you decide to have it. That's you've got those years on top. And our local example here, as you all know, they applied for a permit. So this is Hinkley Point C. They applied for a permit in 2008. Construction started in 2017. It was supposed to cost 16 billion. It ended up costing 26 billion. And the total time was 19 years, 19 years if it starts on time. Okay, there's still ample possibilities for delays. So these aren't 3 random or 3 ones I've particularly chosen because they were bad. These were the last 3 power stations to be built or being built. Okay, this is the state of the art at the moment. And here's a bonus one. I like this one. This is the Virgil C nuclear power stations, unit 2 and 3. You can see there they applied for a permit in 2008. Construction started in 2013. It was predicted to start a few years ago at a cost of 9 billion. Well, they spent the 9 billion, but they didn't get a power station. They just stopped. Okay. Eventually, it all ballooned to at least 25 billion. The actual money spent was 9 billion. So the lovely people of Fairfield County, South Carolina, are going to be spending the next few decades paying off a bill for an object, for a white elephant, so something that doesn't even produce any energy. Okay, delays, incorrect parts, thousands of engineering changes, billions of dollars wasted. That was one of the quotes. So, yeah, not a great track record. So let's have a look at what happens when things go well. Okay, so this is the standard historical price for manufactured items, for objects. It doesn't work for services quite as well because humans are expensive, but objects are cheap. So if we look at computer memory and storage, you can see this sort of catastrophic catastrophic decrease. It's not really catastrophic. This excellent, this amazing decrease in the cost of objects. So the cost of memory in 1953, if you actually bought 1 megabyte, it would have cost you. I'm pretty sure this is in today's money, £100 million. Okay, and now it costs, oh God, you can't even, what, a fraction of a dollar. So a fraction of a cent for the same megabytes. So, you know, this is an amazing decrease. And you see that on the right-hand side, this is a logarithmic scale. So that's the typical thing that happens. Not everything is so amazing, but another amazing one is lithium-ion batteries. You can see again this decrease over time from 1992. You'd have spent $5,000 for what are we looking at, a kilowatt hour of storage. Now, well, I don't even have the thing for now, but we're at less than $200. So again, a logarithmic scale, and we've got a massive increase in the capacity, the total capacity of lithium-ion batteries. Nuclear bucks the trend. We're proud of nuclear. Nuclear is, well, it's probably not the only one, but it's one of the major ones, one of the few where every year, or every generation, it gets more expensive than the previous generation. Okay, so actually, it's hard to see a trend there. It's not really going up. It's always been bad. It's always been expensive, and it's just stayed expensive. Okay, there was a period in the 60s and early 70s when it was still relatively cheap, but since the 70s, it's just been going up and up. Okay, and why is that? Well, one of the main reasons is we only really build prototypes. Okay, we only build the one of a kind, the first of its kind. And prototypes are really expensive because everything that can go wrong goes wrong. And the reason this is so important is because 75% of the cost of nuclear energy is actually in its construction cost. Okay, so you want to get these down. So why is this so bad? So there's a thing called technology readiness level. Apparently, I think it was devised by NASA, but it's been employed by everyone. It's a scale from 1 to 10, and it corresponds to where you are on a piece of technology. Okay, so TRLs 1 and 2, which I've called stage 1. I've lost the word stage. What I've called stage 1 is a papered design. Okay, that's the sort of thing that us well, how would you call us? Theorists love doing. We work it out on a piece of paper, we run some numerics, and we say, yeah, it works, that's fine. Okay. Stage 2 would be a proof of concept. Okay, so you would build a small machine to test that it works. Stage 3 will be the prototype machine. So this is a fully sized functional machine to demonstrate that it can work in practice. And this prototype will be much more expensive than the commercial version. The TRL, so stage 4, we build several commercial machines. Full production of the machines are built to the same design to keep costs low. Okay, and then over a long period of time, once you've got past stage 4 and you go into stage 5, you get to large-scale productions, economies of scale, competition, and innovation in manufacturing just drive prices down and down. So this is where we want to be. And you'll listen to the people who talk about nuclear power in conferences on nuclear power, and they all say, we need to get to stage 5. They don't call it that, but they say we need to get manufacturing, drive prices down. But the history of nuclear power, well, certainly in the UK, we've only ever built prototypes. We've only ever got to stage 3. Pretty much all the nuclear power stations we have are one of a kind, okay? Because they've all, brilliant new design, let's build this one. We build it once and we never build any more, which is why they're so expensive here. Why does it take so long? Why does nuclear power never get to stage 5? Well, they're big and complicated, okay, and they're expensive and they take a long time to build. So just the testing is really difficult. There's extreme safety precautions, okay? We can't just build it in a university. You can't, BNFL can't come to Lancaster University and say, can you build us a prototype? We're just not allowed to. We don't have the safety equipment. We can build small bits of nuclear material, but not a nuclear reactor. This is a crucial one. There's a small market. We just don't need that many nuclear power stations. We'll see later that France built 58. That was all they needed to power almost all their energy. Each experiment takes decades, years or decades, really decades. So to just do one experiment might take a decade. If you compare that to the experiments we do in the physics department, what's it going to be? It's going to be a year's program to set something, design something, set it up. It's unexportable. Well, okay, we might export to France, France might export to us, but really, we don't share our nuclear technology. We won't export to Iran. And can you imagine, if we exported to Iran, we'll say, okay, you can have this nuclear power station, but we're going to have the US Army surrounding it to make sure that you don't go in. And we're going to have a whole, they just won't let us do that. And, we certainly won't say, well, here, have some weapons grade nuclear fuel for your nuclear power station. It just can't be done. It can only be tested in government labs. So we've got a big lab, I forget where it is, it's somewhere near London, where they do all this nuclear testing, but I can't pop along and see what's going on. It's very high security. Staff have to be vetted for national security and no mental health issues. There's limited sharing of knowledge. So unlike, I'm sure everybody is reverse engineering everybody else's solar panels or batteries, okay? And the underlying knowledge is all shared on the internet and stuff. So we share information for most things, certainly batteries and solar panels and stuff, but you can't really do that with nuclear power because of the commercial, security and commercial reasons. And even just to do a test facility, you need to get the national regulator approval and possibly even the international, the IEA approval. So everything is delayed. Everything takes time. So just doing the experiments takes so much time. What about France? Now, France is really the exception that proves the rule. Okay, so it's always used as the example to how to decarbonize electricity. So a very top-down government approach. The government said, right, we're going to go for nuclear power. We're going to do one design. We're going to build the maximum we can have, which I think is 75 or 80%. They were allowed themselves to build. So they really did well. They managed to get to point 4, stage 4 on my thing where you build several machines, okay, full production, all of the same design to minimize cost. Okay, so they built 58 reactors, very successful, and then it stopped. Okay, all the engineers moved on to other jobs. They didn't need any more reactors. There was nothing for them to do. They then retired and all that knowledge was lost. Okay, so we came along in probably in the 1990s, certainly the 2000s, and thought, hey, the French are very good at building nuclear power stations. Why don't we employ the French to build our nuclear power station? It didn't go quite so well. Okay, and of course there's a hidden cost. They're all running out of steam now. They're all coming to the end of their lives. They all need decommissioning. The EDF estimates it's going to take 22 billion euros. Their estimated cost is a quarter of our estimated cost. Okay, so the reality is probably somewhere in between, but it could be 4 times higher. So in a sense, they've borrowed their cheap energy because they still need to pay back that. That's not, that decommissioning cost hasn't been saved. So what happens if we were to decide to go nuclear? So let's say the UK decides tomorrow we're going to build nuclear power stations, build our way to carbon neutrality. Okay, so it's been estimated it would cost 350 billion to decarbonize the electricity grid, or 1 trillion to decarbonize all energy. So we'd be looking to building 12 to 36 Hinkley points. But we would not see a single kilowatt hour of this electricity for 17 years, because that's basically how long it takes. And that's assuming we can get the regulations through quicker and the planning permission and all those things that we're very good at in the UK. What would we be replacing after 17 years? Well, there's no point replacing renewables because they're already generating low carbon power. And if we were to burn oil, gas, coal for 17 years, well, we don't burn coal anymore, but this would make nuclear energy very, very carbon intensive. So when you look at the graphs for nuclear energy and how low carbon it is, bear in mind that's only low carbon once the thing is built. Okay, we're going to wait 17 years where we're burning we're burning gas. Then we get energy. So all that gas, all that carbon has to go in the atmosphere before we see the nuclear plant and the nuclear energy. Now, all of these things I've talked about, this is the standard, what's called traditional standard nuclear. They're all pressurized water reactor. It's a standard design. It's been around, oh God, since the 50s, certainly. And we've all settled on this design. But there's always new nuclear. Okay, so all existing commercial reactors are pressurized water reactors. They're big, expensive, and they take about 17 years to build. Okay, by contrast, new nuclear will be, so this is what you get when you watch YouTube videos, especially too many. Okay, they'll be cheap. They'll be small in design, so they'll be mass produced, and it will get to stage 5 on the technology scale. Okay, so you'll get that driving down of prices. They'll be quick to build because we're mass producing them. They'll be clean. So this is what I say, they'll have a much higher burn up of fuel. So instead of burning, so standard PWR will burn about 5% of its fuel. The rest of the fuel becomes highly contaminated with plutonium. It's a nightmare. But these will burn up all their fuel, so there'll be much less high-level waste. And the waste, at least in some cases, will only last hundreds of years rather than millions of years. You won't have this plutonium problem. They'll be safe by design. Okay, they're inherently safe. So the laws of physics actually prevent them from running away. Okay, and at least on paper, this is true. So all new power stations, they don't have to be actively controlled. The more they generate energy, the hotter they get, and it then stops the reaction going. So they keep at a stable point. Okay, and in some cases, the fuel is molten. It's already molten, so there's no possibility of a meltdown. It's designed to be molten. Non-proliferation. They all claim that there's no way the fuel can be turned into weapons, or any of the fuel or the waste products can be turned into weapons. They can follow the demand of the energy. So as the energy goes up and down during the day, they can use them more or less as required. They can be sent to developing countries really easily to provide power, to lift them out of poverty. So this one makes me feel a bit ill, actually, when I listen to them talking about this, because I think, no, it's not. It's not going to help, unfortunately. And finally, they can be used to burn up existing nuclear waste. Okay, so you put your waste in, and it converts it from these things that take millions of years to things that only last 100 years. So I've heard all of this. Okay. And there's lots and lots of new designs, okay? So there's small modular reactors, SMRs, molten salt reactors, MSRs, sodium fast reactors, lead-cooled fast reactors, accelerator-driven subcritical reactors. This is what the Cockcroft was interested in a while, so I knew a little bit about this. Thor and breeder reactors, and many combine several of these. So the liquid lifter, this is called, liquid fuel thorium reactor, is, for example, a thorium-based SMR MSR. Okay, they love their acronyms. Notice they never use the word nuclear in their title. They love the acronyms. They're not so keen on the word nuclear. Okay, where are they on this technology scale? Okay, have any of them got to mass production? No. Have any of them been to the case where we at least build several of them? No. Two of them might, you can claim, be prototypes. Okay, I think there's a prototype sodium fast reactor, or there have been ones. There's a prototype small modular reactor sitting on in a outside. Well, we'll see it. Some of them have got proof of concept. So there's the small modular reactor certainly has some proof of concepts. The molten salt, well, there was one or couple of experiments being done. The sodium fast reactor, I think that's had a proof of concept. Okay, I don't know about the lead fast reactor, but they all work on paper. So they're all paper ones. Okay, so most of these are only on paper. Some of them will have proof of concept. Each experiment takes years or decades and costs billions. In a few cases there has been a prototype. A realistic time frame for these technologies is, well, maybe 10 to 15 years for a proof of concept, another 10 to 15 years for prototyping, plus another 10 to 15 years for several to be built. So if this is the answer to our climate change, this is not climate change now, this is climate change maybe 2060, maybe 2100, I don't know, 2100. Passive safety doesn't really mean the reactor is safe. So recall Fukushima, the reactor actually shut down as soon as the earthquake hit. Okay, so all the passive safety, or whether it's passive or active, I don't know, but it hit, but it switched off immediately. However, the problem was that the decay products then produced lots and lots of heat, and this caused the explosion because they could not be cooled. Okay, so passive safety by itself is not sufficient. The SMRs, so the idea is that you send SMRs to developing countries who don't, but I don't think we should be sending them to countries who don't have nuclear expertise. They need to create a new regulator, train local experts so that they can run the nuclear power stations. So I'm going to go for two of what I believe is the best cases, the small modular reactors, which are actually a PWR type, and the thorium molten salt reactor, because they're the ones that are receiving so much hype at the moment. So the small modular reactor, so here, can anyone speak Russian? Where is it? Oh no, but at least you can. Academic Lomonosov, Pevek Harbor, Russia. Okay, so that is it's actually a prototype small modular reactor. They built it. The cost was 500 million pounds. It was 3 times over budget, just like everything else is in this world. So small modular reactor is technically anything that is less than 300 megawatts electric, compared with over 1,000 for a normal power station, so they're roughly a third of the size. They apply to many, many different designs. The idea is that we build lots and lots of them so we can get to the stage 5 where the prices come down. They'll be mass produced. They will use designs that are passively safe with no possibility of proliferation to keep costs down. We can build SMRs. So we've been building them for years for submarines. And there's a prototype, as you can see, already in operation. So the big promoter of this is Rolls-Royce, which claims to be able to build a PWR, a pressurized water reactor, small molten reactor for 1.8 billion, which is 3.8 million per megawatt of electric, compared to double that price for Sizewell C. So that's for their 5th unit. So the idea is the first one's really expensive and then they come down. We've heard this one before, haven't we? The first is really expensive, but don't worry, because the later ones will come down in price. Okay, but all SMRs actually really cost billions. They're prototypes. There's no sign of any saving from mass production. These are the prototypes. They will really need active as well as passive safety. So that's adding to cost. It means that human beings need to be on site. These ones are really being proposed that they are walk away safe. Literally nobody has to be there. So the SMRs in nuclear submarines, I hadn't realized this, but they actually use, current ones made by Rolls-Royce, use weapons grade uranium, so we can hardly ship that to lots of different countries. The Rolls-Royce is still on paper, okay, and as I say, given nuclear energy's track record, this was expect this for years. In 2018, the SMR asked for a few billion from the government to support their finances for the first of a kind project. Okay, so the money is not going in taxes, coming from the energy, coming in taxes and going to the government. The money is money moving from the government into these projects, maybe for decades before anything comes out of it. And the nuclear regulators may and should actually demand active safety as well as passive safety, which will add to costs. I like my nuclear reactors to be big, okay? I like the fact that when I look out of the window every morning from anywhere in Lancashire, I can see Heysham Power Station, okay? Why? Okay, I don't, they're ugly as anything, but it means that they can employ people who are paranoid about safety. It means the IAEA know exactly where they are, and they can send inspectors around to check that they're working correctly and no nuclear fuel has, quote, gone missing. Okay, that's quite important. You're not going to get that for small nuclear reactors. They're big for a reason. There's economies of scales. Why do we build such big ones? Well, because the economies of scales keep the cost down. Okay, if you look at the list of benefits, don't read them as, so we'll go back to the benefits. Where are we? Here we go. Go back to the benefits. Don't read them as this is what they will deliver. Read it as this is a list of things that they have to deliver, otherwise this technology is never going to work. Okay? They have to be cheap, obviously, because they're competing, you've not got the economies of scale. They have to be quick to build. The clean's not so important. They have to be safe. They have to be inherently safe, because if you need a team of people plus IAEA inspectors constantly there, it's just going to push the price up. They have to be non-proliferation. Otherwise, as I say, all the regulators are going to get worried. Okay, so those lists is not so much what you need, what they will deliver, but what they need to happen before they will work. Rolls-Royce, so there was an analysis of this where they looked at Rolls-Royce proposal, which came out a few years ago, and they said, well, hold on a minute, you only get these economies of scale if you build lots and lots of them. But the problem is, who are you going to sell them to? You see, we really only want to build British ones. The French only want to buy French ones. The Chinese will only buy Chinese ones. The Russians will only buy Russian ones. Okay, there's not much opportunity to export, and so you end up with a lot of monopolies. Okay, this is not going to drive down prices, and as I say, ultimately everything is mainly a paper design. Okay, so let's look at thorium. The thorium fuel, liquid fuel thorium reactor. Okay, so this was a this has created a lot of buzz. Okay, people are very excited about this. Okay, thorium is a fertile fuel. Okay, which means it doesn't itself undergo nuclear fission. However, if it catches a neutron, it becomes uranium U-233, which is fissile. So similar to uranium-238, which is fertile but not fissile. But when it catches a neutron, it becomes plutonium-239. Okay, so the idea is that you start with your thorium, you fire, it takes some of the neutrons that are created by previous fission. Okay, it's converted to uranium-233, which can then undergo more fission. It can be used for many types of reactors, so it is being used at the moment and being tested in India in a standard pressurized water reactor, but the excitement is about the molten salt reactor. Okay, so in a molten salt reactor, you create the fluorides of thorium and uranium, you heat them to 700 degrees, okay, and the fuel is a liquid, so it also acts as a coolant, so you get lots and lots of advantages. And up here you see the test facility that was built at Oak Ridge laboratory, and probably the second one that ran from 1966 to 1969. So there has been a prototype. Okay, China has an active molten salt program reactor starting in 2011, and it's being tested now, and it costs the Chinese, what claims it costs the Chinese 200 million. Okay, I believe the Czech Republic is building one, but the details are sketchy, and there's lots and lots of other proposals around the world. Okay, again, loads number of benefits. It's cheap. Again, mass production, it's small and so on. It's clean, it will burn up much more of the fuel. It's inherently safe because if you look at this design here, there's a plug. Okay, if that, if it stops, that's actively cooled. So if there's any problems, the cooling will shut off, and that will just drain into these specially designed tanks where the reaction will stop, and it will just solidify. It's non-proliferation. The fuel cannot be turned into weapons because the uranium-233 is contaminated by uranium-232, which produces a high energy gamma ray, making it too dangerous to handle. They can follow demand. You can turn them up and down as the energy is required. And then allegedly they can be sent to developing countries to provide power to lift them out of poverty, as we said, and they can burn up existing nuclear waste. Okay, getting into the weeds, okay, what's the problems? Okay, so there's loads of problems. The pipes need to contain 700 degrees centigrade acid with a high neutron flux. We just don't have materials that do this. The neutron flux apparently in brittle metal, so they make them really bad, and we certainly don't want any leaks. Okay, we don't know how long the pumps will last. The pumps fail all the time in this very, very harsh environment. In fact, we don't even know how to measure the flow rate, which is an important quantity. During the Oak Ridge plant's lifetime, the molten salt reactor was shut down 225 times, only 58 were planned. Okay, so it's not exactly a working prototype. And Oak Ridge was not shut down because of worries, because it wouldn't produce nuclear weapons. It was shut down for persistent failures. However, and this is going to be my tagline, humans are bright. If we throw enough money at it, and clever physicists and engineers will probably solve these problems, but it may take a few decades. Okay, so it can be solved. The Chinese MSR is not expected to run continuously for more than 30 days at a time. And also, they're not particularly keen on sharing all the information they've gathered. Okay, so we'd have to do our own. What about non-proliferation? Well, they've got a protactinium problem. Okay, I don't say that word very often, although I have recently. Okay, so you can build nuclear bombs using UT-33, so that's the fuel. Okay, and several have been detonated. Okay, so the US detonated one in 1955 and the Indians detonated one in 1998. But we don't have to worry because the U-233 is contaminated with the U-232, which produces this dangerous gamma rays. But there's a really easy solution to this, okay, apparently. So technical, this is the only technical bit of the talk. When thorium-232 captures a neutron, it quickly decays into protactinium-233. After a half-life of 27 days, it decays into uranium-233. The contaminating protactinium-232 decays into uranium-232 after only 1.3 days. So remember, this is the one that we want. This is the one that causes a problem. So you don't take the uranium, which is contaminated. You take the protactinium out, which they can do, because it's already molten. It's really easy to remove. Okay. You wait a week or so that all the bad stuff, all the UT32 has already been created. Okay, you can extract that out. That's also really easy to do. And then you wait a couple of months for your lovely bomb-making U-233 with no contamination. And as I say, humans are bright. If we throw enough money and clever physicists at engineers, or I should say, if they throw enough money and clever physicists at this, they will probably solve these problems. Okay, this is not. There's no way you can say that this is not. This is non-proliferation. You can certainly get weapons-grade uranium from this. There's more problems. So a UK experimental MSR would probably take at least 10 years. Cost $1 billion. So this will just be stage 2. Of course, you then got another 15 years on top to get you to stage 3 and so on. Okay. I've just guessed these numbers because of the UK's propensity for bureaucracy. I would imagine it would take much longer. The Wikipedia page, good source of information. So that lists 22 problems associated with this technology, potential problems. There's also protactinium-231, which has a half-life of 32,000 years. So we're going to have, there'll be long-term radioactivity. Reaching breakpoint of the number of neutrons, whether you can even do it is questionable. There's a beryllium toxicity, there's limited graphic lifetime, and ... Just go on that site. However, humans are bright. If we throw enough money and clever physicists, I'm sure we'll solve these problems. Okay, these are solvable problems. It will just take a long time and a lot of money. So what about renewables? Okay, see if I can finish by 8 o'clock. If I finish at 8, is that okay? And then there's time for questions? Okay, brilliant. So can renewables and storage solve the energy and climate crisis? Yes, but it's going to be difficult, okay? So currently wind and solar can do it, but we need to be better and have an increase in efficiency, but we're better to have an increase in efficiency. Energy storage is not up to it yet. There are lots of proposed solutions. I've listed a few there. Improved batteries, the CO2 battery, that's just a store of CO2. They compress it when you've got energy and they let it release when you need it. That's a gravity battery, that's a flow battery. You've got hydrogen fuel cells. So there's lots and lots of ideas. The point being that these are ideas that are easy and cheap to test, or relatively cheap to test. You can test them in years rather than decades. We will find these solutions. As I say, humans, will they all work? No, of course they won't all work. Some of them will. If we throw enough money and clever physicists and engineers at this, we will solve these problems. And we will solve them in a lot less than 10 years. The other thing they don't really tell you about is that nuclear power needs energy storage. It's something called, who's heard of the duck curve? Okay, oh, excellent. Okay, so we have nuclear power because the sun doesn't, we have to have nuclear power because the sun doesn't always shine and the wind doesn't always blow. And here's the energy demand over the day. So you see, so this is California, okay, which is a very sunny place. And it used to be reasonably constant during the day, this gray curve. But as we've got more and more solar energy, the demand during the day has decreased. Okay, and you can imagine this is going to keep going down. You can get to a point where there is no base load. So if you're only replacing the base load, well, maybe you don't need it at all. But if you're balancing, if you're building enough nuclear capacity for the whole lot, then you have to be right up here, which means you've got a lot of nuclear power stations which is just idling around, not doing very much. Okay, they need energy storage, they need load balancing. In fact, we've always known this. Who recognizes this place? Okay, that's the Welsh Nuclear Mountain. Okay, that was built in the 80s. I remember it being advertised. Okay, and why did we build it? Because we needed to store the energy from nuclear power and coal at the time to release when it was needed later. Who recognise this? Okay, some very old people will recognise Economy 7. Okay, we were encouraged to use to heat our storage facility, not for storage, water during the night because the electricity was cheap. Okay, so we're demand balancing, we're storing energy. So nuclear power stations can track demand, but in a sense, you've already paid for that electricity. 75% of the cost of that electricity you've paid for. So even though you're not using it. So my analogy is like saying you bought a Ferrari with a car loan. Your wife screams at you and says, you are not going to drive, you're going to have to save money. You're not allowed to drive it. So you let it sit in the garage and you're saving money because you're not using any fuel. Yes, but you're paying 3/4 of the cost of it through the car loan anyway. So you're not really saving any money. And the same is true here. What about land? So land is a real issue with renewables. And I'm afraid I don't really know the solution. This might be the killer. Okay, there's a real problem with the amount of land that renewables need. And if done badly, we will basically cover most of Britain with solar farms and wind turbines. Okay. However, agrivoltaics combine solar panel and farming. So there's a picture here. It's brilliant because, well, certain crops, it's really good. It replaces polytunnels. So you get all those sensitive crops will grow brilliantly under solar panels because they don't like too much sunshine. So you can do this. You can cover a lot of land with solar panels and still use it. Okay. What about that should say a 2 megawatt wind turbine. So I missed that out. Well, it uses 0.5 kilometer, but most of that can be used for other stuff. Only 600 square meters of it is land used for not just the concrete base, but also the power substation and the access road. Okay, so you can have all three in one place. You can have the agrivoltaic, so you've got you're growing crops, you've got the photovoltaics, and if you get permission, you can also put a few wind turbines up there, and you're getting everything from the same place. There's also energy islands have been proposed where you build an artificial island out at sea. Denmark's proposing to do one at the moment, and you use it and you fill it. You put your wind turbines out at sea with that, and so you use that as an energy island. The one I like in terms of local, one sheep is the equivalent of 5 to 10 houses worth of energy. Okay, to give you an idea of how much land we use just for raising animals. Now, being a vegetarian, I'd be happy to reduce the population of sheep, but other people might feel less keen on that one. So what is the future? Okay, what should we do about nuclear power? Well, for a start, don't close the nuclear power stations we've already got, okay, if they're running safe enough, okay? It's a big if, because Pilgrim Nuclear Power Station actually closed when it had to renew its license, and the nuclear regulator says, yeah, you can renew your license, but you have to do these changes. And basically they had to make it earthquake proof and stop draining lots and lots of water. And it was too expensive, so they closed it down. Don't start building any nuclear power stations, okay? We're going to have to carry on with Hinkley Point C. We've sank too much money in there, but you can certainly cancel Sizewell C. Be honest about the timescale for new nuclear, okay? Let's quickly go to the U2 site. So here is, I can't remember his name, okay, talking about nuclear power, and you get 10 seconds or 15 seconds.
We could do a better job. What he built was a reactor based on molten salt rather than water. A light water reactor uses water as its primary coolant. It wants to turn to steam. Now, if you get over 100 degrees C at 1 atmosphere, your water will turn to steam. But 100 degrees C is not hot enough to generate power, really. So they get it up to 300 degrees C, but to keep it liquid, they have to put it under 160 bar pressure.
Okay, so there he's talking about the molten salt reactor. Basically, that's all he talks about the reactor. He's selling this equipment as though you could go to, you know, Amazon.com or whatever and just buy one. Okay, he doesn't tell his audience, yeah, this existed, didn't as a prototype, it didn't work very well, and it's 30 years away before we'll build it for you. But he doesn't mention that. Okay, so let's be honest about how long it's going to take. Now, this might surprise you after this talk, but I would say that the UK should actually invest in new nuclear, possibly Lifter, the thorium one, but as part of an international research program where knowledge is freely exchanged. So we just have to do it once rather than each country doing it by itself. The UK could in principle have joined the Czech Lifter program, but there's problems because it would need an international agreement because we're no longer a member of the European Research Council or Euratom. So that might cause a problem. By the way, nuclear fusion won't solve the problem either, okay? Again, nuclear fusion, I like the way it's done. It's done as big international collaborations where the knowledge is exchanged, but both fission and fusion are going to be solutions for 2100, really, rather than for now. What about renewables? Well, the UK could stop, it should stop the almost complete ban on PVs and wind farms, okay? You just can't get, well, it's very hard to get permission to build a wind farm now on land, okay? They should do a massive investment in the energy grid. They should clean up hydrogen. Let's have loads of green hydrogen facilities to use the excess electricity that hopefully we're going to be producing. And these should mainly be used for fertilizer production, but also energy storage. In my opinion, I would say my goal, if I was a politician, would be to aim for 120%. So I think that we should aim that at peak production, we're producing way more energy, electrical energy than we need, so that we can store this. Obviously, a massive increase into R&D into renewables and energy storage. The things you all hear about: insulate homes, promote heat pumps, train an army of engineers who understand and promote these. If you go to an engineer and you say, I want a boiler, they'll stick in a gas boiler. They won't stick in a heat pump. Okay, we should be training these people up so that they will promote these. And encourage energy-based storage and production. So I've put a link here to Brumpton 2.0, which is Phil Furno's organization near Kendal, where they're hoping to to create a community-based energy program. So, in summary, nuclear power will not solve the energy crisis or the climate crisis because it will just take too long. Renewables can, but it will be hard work and will need lots of investment. And nuclear power will suck up this investment. So thank you. And now before we do any more questions, I wonder if I can quickly, where am I? How do I do this? No. Okay. Just thinking. Right. Present. Okay. So please vote on whether so the top one is where you think that nuclear power is not part of the answer. The bottom ones are whether you think nuclear power has been is part of the answer. And then there's I think that nuclear my mind has changed, or my mind has not changed, or I hadn't really thought about it before. Okay. So I wonder if I've managed to change anybody's mind. It'd be interesting to know. Oh, I'm going the wrong way here. I've managed to convince somebody that nuclear power is the answer. That's not good. Okay, maybe we should just let that run in the background if I can work that out, and ask anyone if there's any questions. Maybe, okay, there'll be time for maybe a bit of a debate as well. Thank you.